Alright, so welcome. Again, the name is Mr. Thomas, founder of Buckle Down Tutoring Services. We have been having our series. Here's part 3 to our series where we discuss do a revision of the topics in CSEC chemistry. We're going to dive right into it. Now it says define each of the following. So what's an atom? An atom is basically the smallest. Usually in some textbooks, in some online literature, you may see it as the building block of elements. So it's the smallest particle of an element that can exist, and while it is existing, it still has the properties of that element. Now, the other term is mass number. When we think of the mass number, think about those subatomic particles that are in the atom. And we should know that what contributes to the mass number is the number of protons and the number of neutrons. So when you add these together, that's how we get the mass number. Now again, in some books, you may see them referring it to as being the nucleon number. And it's referred to as the nucleon number because both these subatomic particles are actually located in the nucleus of the atom. So if you see that, don't be, frightened. The next term would have been the atomic number. And I say to students, the atomic number or the proton number is the signature of an element. No two elements has the same atomic number. A matter of fact, when you move towards, when we're going to be doing the topic of the periodic table revision, you'll recognize that the elements, they are now in order based on the atomic number. So the number of protons. And so the number of protons for an element or an atom, it doesn't change. Meaning, if you're doing CSEC, only you alone will have the candidate's number. Whether you're in Jamaica, Trinidad, Barbados, Guyana, only one person will be assigned a particular candidate's number. So they might not know you by name. So they won't know you as a Damian Thomas, but they will know you as 1105692. And so the atomic number is like the signature of the element. When we look at a relative atomic mass, it's really the average mass of one atom of an element, and they compare it to the mass of 1/12 of a carbon atom. So a carbon 12 atom, that's how we basically come up with the relative atomic mass. In this table, we are supposed to complete the table with the information. Now we have particle, which is the proton. We talk about the subatomic particles, 3 subatomic particles: proton, electron, and neutron. The relative charge of a proton is +1. And so inside of the nucleus has a positive charge. Why is that? Later on we recognize, if I jump to the bottom of the table, we're not seeing the particle, but that is the neutron. And the neutron has a charge of 0. Now while they're in the same location, can you remember where? If you said the nucleus, then you're correct. They're in the nucleus, and so because the proton is the one that has the positive charge, and naturally the neutron, they don't have any charge, considered to be neutral, they are emitting the charge of the proton. So there's this positiveness in the nucleus of an atom, and that's due to the proton. Location, just mention it. They are located in the nucleus. For the electron, the mass is like 1 over 870. And maybe I should say 1 divided by 1870. So it's really insignificant when it comes on to the mass. And of course, the mass of a neutron is 1. And as a student, you should now make the link as to why the mass number is a reflection of the protons and neutrons and not the electrons. Because those two subatomic particles, they are the ones adding to the mass of the atom, not the electron. When you look at the relative charge of the electron, it's negative. Let's visit the protons. We said the protons were, and if you said positive, you would have gotten that right. Now, what I want you to understand as a chemistry student, whenever CSEC mentions atom, so they say the atom of magnesium, an atom of nitrogen, an atom of carbon. Once you're dealing with the atom, you should know that the atom is neutral. So all atoms are actually neutral. Why? You see, the thing about atoms, they have the equal number of protons. So I tell my students, when you're going to be doing atomic structure, if CSEC is going to be putting a question in terms of atomic structure or bonding, they will select elements from the first 20. And so if you know the atomic number, that puts you at an advantage. Why am I mentioning this? So the proton, if you know the proton of an atom or an element, like for example magnesium, do you know the atomic number? If you said 12, you're correct. Which means magnesium also has 12 electrons. Now let me be specific. The magnesium atom also has 12 electrons. Which means the protons, which are positively charged, and the electrons, which are negatively charged, they are canceling out each other, and so an atom is considered to be neutral. The location of the electron. The electrons are located in what we call the shell. So we use that term, the shell. We also refer to them as being the energy level. So different energy level can accommodate different amounts of electron. And we'll get into that later. The neutron. We said the neutron is located also in the nucleus. And what you can actually notice based on this, if you look back for magnesium, the mass number for magnesium is actually 24. The atomic number is 12. Now each of these is adding to the mass. So the neutrons, their mass is actually 1, just like the proton. So when you look at the relative mass of the 12 neutron and the 12 proton, that is where the 24 is coming from. And so if as a student doing the chemistry, if you can make this little connection, you will appreciate the mass numbers, the atomic number, and the number of neutrons more. So magnesium has a mass number, atomic mass of 24. The number of protons are 12. The number of neutrons 12. So both of them come together to provide you with that overall atomic mass of the element or of that magnesium atom. Now, some literature, some books, you may see them represent elements and the information for the elements differently. But learn this, for your CXE, once they're giving you a question, once you're being asked a question, if you look at this diagram or this representation, the nuclear notation can be used to represent the atom. This is the way one CXC is giving you questions about atoms or any other topic that will have the display of the symbol and other information about an atom. This is the form that it will come in. So state what each letter represents. Starting with A. A would have been your mass number, your atomic mass. So when we spoke about magnesium earlier on, do you remember the mass number? Yes, 24. That 24 will be right at the location where you're seeing A. So automatically, once you see a representation of this sent by CXC, you should make the connection as to what these numbers represent. B is the atomic number. So sometimes you're looking on the internet and you may see a periodic table, and the periodic table probably put the mass number at the bottom and the atomic number at the top, vice versa. What may the case be? Bear in mind for CXC, once they're giving you information, this is the representation that it will come in. Then of course, X is the symbol. Now, let me just jump to the table right here to show you something about the symbol. Two things I want to point out. One, the symbol doesn't always reflect the name of the atom or the element. One of the reasons, because some of these are coming from the Latin name, right? And some we use the English name. So that's something that influenced the symbol. No two elements would have the same symbol. Now, if an element, and this is very important, has one letter representing the symbol of that element, that letter, when you're writing it, should be a capital letter. If you have two letters representing the symbol of that element, like for example zinc, you should have the first one being a capital and the second one being a common. As I said before, not all the elements are able to have a reflection of the first or the second letter representing the symbol, because it gets its name from also the different language. So when you see lead, you might have thought that it would have been L, but lead is actually Pb. So while X there would represent the symbol of the element. And we have seen, if you look at the next question, we're seeing various representation of this coming out. So it says, using the nuclear notation given, fill in the spaces in the table below. Right? So the first one, or we can start by all of them and just deducing the information. Starting with the name of the element, P represents, and you should know the first 20, but outside of you knowing the first 20, and I want to make it clear, because some students have this misconception. When we say the first 20, it's for a specific question. So the atomic structure question and the bonding question, that's where CXE will bring the first 20 from. Bear in mind, you are going to have to be familiar with others, and here are prime examples that are not in the range of the 20, but they will be coming up in different topics that you will be covering over the syllabus. So when we see a P, a lot of times students make a misconception. So when we look across, so as we said, even though we have those 20 elements that we're going to be zeroing on. Once you get a question from atomic structure, they won't ask you to show bonding or draw the structure outside of those 20, right? So that's where the 20 comes in. So students, here we have an element, name of it, P. Sometimes it's confused to say that it's potassium. No, it's phosphorus. Potassium is actually, yes, you said it, K. Note as well that it's a capital letter, right? Followed by zinc, Zn, followed by lead, followed by silver. Now silver is another one where it doesn't, you would have maybe think S, there's something, which other element or which element has the symbol S? Yes, you said it's sulfur. And you said, why not, since it's silver, why not Si? There's also another element by having the symbol Si already, which is silicon. And so, as I said before, no two elements would have the same symbol. Number of protons, and I want to bring it up a little bit. So when we look, remember the notation here, I'm not sure if you're seeing it clearly. This is a 15, and so the number of protons is 15. This is the atomic number. Remember, the atomic number tells you the number of protons. Are you able to tell me how many protons are there for zinc? Yes, correct. 30. How much protons are there for lead? Definitely 82. How many protons are there for silver? You got it right, 47. Now, while we note that this representation, the nuclear notation, it doesn't give any information about the neutrons, but you can use something to find out how many neutrons there are present, because we know the mass number is a combination of the number of protons and neutrons, while the atomic number is the number of protons. So you can write down this formula. Whenever you want to figure out or find out the number of neutrons in the element, you subtract the atomic number or the number of protons from the mass number. So, prime example, you have 31 as the mass number, which simply means that in this 31, you have the contributing to the mass is the protons and the neutrons. If we know from the atomic number that we have 15 protons, so we recognize that if we want to get the total number of neutrons, we subtract that atomic number from the mass number. So when we subtract the 15 from the 31, we would have gotten 16. 30, subtract, when you subtract 30 from 65, yes, 35. When you subtract 207, or rather, when you subtract 82 from 207, comment below, what's the answer? That's right. When you subtract 47 from 108, great. Now, as I said before, you should have your workbooks and you should be filling in the answers as we go along, or you can watch the video, then you try and complete the various questions on your own. Can you remind me? Think about it. What did I say? How can you know the number of electrons that are in an atom? Now, since we're dealing with the atom, we know that the same number of protons is the same number of electrons. And yes, Sounding like a scratch record, but repetition helps. That is the reason why atoms are considered to be neutral. They don't have any charge, because same number of protons, same number of electrons. And so if I have 15 protons in phosphorus, then I would have 15 electrons also present in phosphorus. And you can do the others and tell me, what do you have for zinc, lead, and silver? Now this table speaks about the atomic symbol, the mass number, the atomic number, the number of protons, the number of electrons, the number of neutrons, and the electronic configuration. And so what I'm going to do, I'm going to zero in on the electronic configuration and some other information about the elements and what you can, how can you use the information to know where these elements are located on your periodic table. So up on over, we're jumping over to a Word document to get it in. So we're on our Word document. You know, magnesium is like my favorite element. The magnesium, what do we know about magnesium in terms of the atomic number? We know the atomic number is equal to 12. Now, in terms of the electronic configuration at year level, what we say to students is that each energy level, remember we spoke about the position of the electrons. If we're talking about the first shell, that shell can house or hold 2 electrons. And then all the other shells after that, and mark you might have to relearn it, but for ease, and I will agree with some of the teachers, we just say all the other shells can hold 8 electrons, right? So usually you go up to about 4 shells. So unfortunately, when you reach to, if you take it to the tape level or college level, when you're doing this information, you might have to relearn a little bit about how many electrons can be housed in a particular shell. But for your level, this is what you need to remember. Now, what is the key thing that you need to take away? And we'll have to just put this into play. You see, the moment you know the atomic number, you will know the amount of electrons. So if you know the first 20 atomic number, you can relate to it and utilize it. Look, I'm going to show you how this can benefit you a lot. So I now know if my atomic number is 12, it simply means that in this atom of magnesium, I also have 12 electrons. Now, when we talk about electronic configuration, is how the electrons are basically represented in the different shells. So the first shell can house 2 electrons. So we put that 2 right there. Now, when we are separating the different shells, we use a comma. So the second shell can house 8 electrons. So how many electrons do we have remaining to fill out? We have 10, because 2 are actually on the first shell. One other thing that you want to bear in mind as well, and you can take it away because it will help you when you're doing your bonding and structure and bonding. Elements, when they have their electrons on their shell, the electrons like to pair up. So the electrons like to have a pair. So the second shell can house 8 electrons. So we have that 8. And again, we have that comma to distinguish between the different shells. So we see in the first shell, we see in the second shell, and now that is total 10 electrons. So we have 2 remaining. So when you look at the electronic configuration of magnesium, we have 2, 8, 2. And this is very vital. Very vital in the sense that the electrons that are on the outer shell, we give them a particular name. We know the name? Definitely, you said it. The valence electrons. And the valence electrons are the ones that are going to be taking part in the chemical reaction, the bonding. So we recognize that we can use this to gather some information about magnesium. Now, CXC doesn't always have to present you with the element. They could have said element X. And if they said element X, then, and having the atomic number, you don't have to struggle to say, you know, trying to figure out what the element is. Maybe the question just asks you to write the electronic configuration for element X if it has the atomic number 12. So understanding the concept is good. So whether it's element X, Y, magnesium, chlorine, whichever element they give you, you can apply that. So each energy level has a certain number of electrons that they can hold. And so we basically just put it, once they have them enough, we basically move on. So think about it like a parking lot for a mall or a plaza. You reach to the parking lot first, you're going to be parking in the slots closest to the plaza so that you can, you know, get in and then you get to the shop or the area that you want to. You want to park on the outskirts and then walk in unless the spaces are filled. So that's how the electrons, we fill the electrons that are closest to the nucleus first, and then we proceed to the other shells. Now, a popular misconception students may do is to continue filling this electron or the shell or putting the 8 on it. It's not to say that it should have the maximum, but it's the amount that is there. Now when we see this 2, as I said before, this represents the valence electrons. So there are 2 electrons in the outer shell of magnesium, which can help you because this number tells you the group that magnesium is in. And so group is group 2. So magnesium is in group 2. And we use Roman numerals. Yeah. The other concept is the period. Any amount of occupied shells. So the amount of shells that have on electrons. So we see shell 1, shell 2, and shell 3. So the period would be period 3. So magnesium, if you want to locate it, it's in group 2, period 3. Now bear in mind, sometimes we lose track of where we can find the element or the group. So once you know the atomic number, I didn't have to look on the periodic table to determine the group or the period that magnesium is in. You can do it for other elements, all the elements, to derive the group and the period. So very vital to when you're actually answering questions. It's a good technique to utilize. The next thing I want to probably add if there's 1, 2, or 3 outside of boron, if you have 1, 2, or 3 on your outer shell, then that element is going to be a metal. Now CXC likes to bring certain questions. So you know the questions are thinking questions. So they might not use magnesium, as I said before. So they said element Q has the atomic number 12. What's the electronic configuration? What group is element Q in? What period is element Q? Or they might say, give me 2 properties of element Q. Now you would have known that when you look at element Q, it has 2 electrons on the outer shell, which means that it's going to be a metal. And so 2 properties of metal, you know, they are solid at room temperature outside of mercury, of course. They have the ability to conduct heat, or they are good conductors of heat and electricity. So person will say, oh, I don't know what element Q. What kind of wickedness this man, my teacher not teach me, I hate him, you know. Teacher not get this, and you start to create that. But you sit on the knowledge that you can utilize to get to your answer. If they have 4, 5, 6, 7, or even 8, and we have to watch with the 8, because we do have helium that has 2, and that is the outer shell for helium. These are considered to be non-metals. Yeah? So the moment I see, if I happen to have another element and I say that the electronic configuration is 2, 6, then I know this 6 saying that the element is in group 6, and so it should have been a non-metal. Properties of non-metal, right? They can be solid, liquid, or gas at room temperature. They are not good conductors of heat and electricity. We know the works. So outside of you being able to tell the group and the period, then you can use a little information to determine if it's a metal or even a non-metal. When you're doing bonding, you're going to take that a little bit further as well. Because we know in terms of, and I'm just, you know, jumping ahead because we have our bonding series to do. If you're a metal, you lose electrons. So automatically, if you have 1, 2, or 3 electrons in your outer shell, you'll be losing those electrons. Alright, so we're not going to dive deep into that because that comes under bonding. And so when we visit back the table, you should be able to now complete this table in terms of the electronic configuration, the number of neutrons, the number of electrons, number of protons, atomic number, mass number, atomic symbol. So I'm going to give you a quick run through. So when we talk about the atomic symbol, we said 1. The atomic symbol doesn't always reflect the element's first letter. It's not always the case. So like iron is actually Fe and not I, because we do have an element with iodine. Yeah? If it has 2 letters, the first letter is a capital, the second letter is a common. The mass number, also known as the nucleon number, because what forms the mass number is the number of protons, number of neutrons coming together, giving you the mass number. They are located in the nucleus, so we call it the nucleon number. The atomic number is the number of protons. The number of protons does not change for an element. So once you have an atom of a particular element, it's a signature. It will always have that number of proton. So by knowing the atomic number, you can even tell the element you're dealing with. Number of protons, as we said, same as the atomic number. Number of electrons, and this is for an atom. So you see, the same number of protons is equal to the same number of electrons in an atom. And because of that, the charge of an atom is neutral. So you won't see a charge. The moment, and you can answer this question, the moment you see a charge, it simply means you're now dealing with an ion. So when we go and look at bonding, that will come up. The number of neutrons, it's not on the nuclear notation, but you can use information from the nuclear notation to get to the number of neutrons. We subtract the atomic number or the number of protons from the mass number. Electronic configuration, it's really a representation of the electrons in the various shell. We said the first shell can house 2, and just for ease, we say all the other shells, 2, 3, and 4, can hold 8 electrons. We say we put the electrons in the shell that is, we fill the shells closer to the nucleus outward. We are supposed to be writing the electronic configuration of these atoms. Bear in mind there is a correction here. You look it up if you note that we have argon, double check the atomic number. So this is just a mistake. We have lithium, and we also have sulfur. Now when we talk about the board diagram, the two-dimensional representation of an atom. When you draw the atom, you draw the circle, and just a case in point, what some persons do is to actually use their compass to create the perfect circle. If you have a compass, you can use it for your exam. Oftentimes I see students drawing the shells, and it's not being done. While it is not art class, please draw them properly. Yeah? It can be neat. The electrons are located on the shell. We need to draw them on the shell. Now the first circle, if you note this, we have the symbol of the element, He, and so we know we're dealing with helium. But here's the thing, another popular mistake that students do is to start to put electrons on this first shell. Now this first circle rather, this first circle is really representing the nucleus. So what is inside of here is the protons and the neutrons. The next circle is representing the first shell. So if it is that you place electrons on this, is not really a correct way to do it. So please draw your circle, then put in your element. If you get a question saying that element X or element Y, that is what you will put. You don't have to try and identify. So you'd have said have an X right here, have a Y, or have a Q. So you are to put in the electrons. Now when you do this, you basically create the radius of an atom. So if you look at these atoms, the radius of them varies, right? And later on when we look at periodic trends and the periodic table, that is going to come, that information when we look at the different groups or the period, you need to make that reference to something like the radii of an atom. Now, when you're putting in the electron, for me as a teacher, because it helps with bonding, you go top. So if we know top and bottom for the aluminum, the first shell, the second shell will have 8. So we go top, bottom, left, right, and then we go top again and we continue clockwise. Now that will help you. You won't see, you might not see the significance now, but when you're doing your bonding, trust me, it makes a whole lot of difference, and it makes it easier for you to actually show bonding, whether covalent or ionic. So practice that. Top, bottom, left, right, and then top, and you continue clockwise. Yeah? So what I want you to do is to try these. Put in the electrons and show what it will look like. Now, as I said before, CSEC for bonding and structure, that is what they would want. So these were drawn for you. If you have the workbook, you are going to draw the circles and the energy shell, the energy levels or the shell for these. You're also going to identify, in each case, identify the element below its nuclear notation, right? You're supposed to do the electronic configuration as well. Or just for argument's sake, you can do the electronic configuration to help you to get some practice, but I really want the name or identify. Now, there is this concept known as isotopy. Now, you have some atoms of the same element. So I'm talking about different atoms of chlorine. And a lot of times, the popular one that you'll see it with is carbon. So most persons can relate to carbon. Carbon and chlorine, we have chlorine 35, chlorine 37, right? We have carbon 12, carbon 13, carbon 14. The thing is, this is when you have a situation where atoms of the same element, they have the same number of protons, because we know that the proton can change. But what is different is the number of, or the mass number is different. Now the mass number is different due to the fact that the neutrons are different. And so, really and truly, CSEC likes to ask this question. In terms of the physical property, how would you describe that of isotopes? Now the physical property is slightly different with these atoms because the mass of these atoms will be different, and so normally we call them by their mass number. So when we say carbon 12 or carbon 14, the 12 is the mass number, the 14. So you see a slight difference in the mass number, so their physical property will be different. And you know, physical property, density, boiling point, melting point. So those things are going to be different. In terms of chemical property, for the isotopes, it's going to be the same. Why? Because while they have different mass numbers, the protons are the same. The protons are the same, which means each atom that's an isotope, they will have the same number of electrons, and the electrons are going to be arranged similar in all of these isotopes. So they will have similar properties. Now, naturally occurring element Y consists of 85% Y23 and 15% Y25. Give the number of protons, neutrons, and electrons in each isotopes of element Y. And all we have to do, we know this information already. When you look, we said can't, and you need to be speaking the chemistry. Say it, talk it. An element will have the same number of protons, same number of electrons once you're talking about the atom. So the 23, 11 protons, 11 electrons, and how we get the neutrons? Definitely, we subtract the 11 from the 23 and we get 12. Now the same concept with Y25. And so you can work out that and put your answers in. So we're supposed to determine the average mass of naturally occurring element Y. And we're going to be doing this and we're going to be talking a little bit about it in terms of the approach. Usually when you hear average, we tend to add up and divide. That's not the way. So I'm going to show you the method. So we're going to switch back to a Word document. All right, so we're back on our Word document. So 85% Y23, 15% Y25. Now, how do we go about finding the average? This is what we do. For the 85, when we talk about percentage, we know we're talking about out of 100 multiplied by the mass number. Normally we talk about that of the element, then we call it by the mass number. 15 divided by 100 times 25. Now if you notice, in terms of percentage, and let me talk about it. If I'm going to be looking for this particular atom in nature, there's an 85% chance that I will see one that has the mass number 23. There's a 15% chance that I will have one that says the 25. Now with this being said, when you do your calculation, usually based on that, the mass number, the average atomic mass that you're going to obtain is going to be closer to the number with the highest percentage. So my atomic mass should be closer to 23 than it is to 25. So that's one little key thing. Also, if you're having a problem, we know that we carry the decimal place 2 places to the left. So if you're a math person, you have 0.85 times 23, it's the same. Also, if you have 0.15 times 25, it is the same. Yeah? So here, bringing up the calculator, and also let me use this opportunity to encourage you, if you're going to be doing CSEC, get those calculators from now, get used to them, and when you're doing your moles, doing your standard form, or to the power expression, you need to be able to understand how to input that information in your calculator and not wait until the day of the exam, then you have challenges. I've seen students who have gotten thrown off due to the fact that they just got their calculator and they're not so familiar with it. So 0.85 times 23 gives me 19.55. Then of course 0.15 times 25 will give me 3.75. And like I said, unlike how you're used to be doing you know, average, you get a test. The teacher says they give you 3 tests, and you want to know your average score, you'll probably add up the percentage that you got, and you would have divided it by 3. Or some tests have a different weight. So your homework have a 40%, your paper 2 have a different percentage. So what we do is to now add these. So 19.55 plus 3.75, and our answer is 23.3. That's the average. And as I said before earlier, your answer is going to be closer to 23 than it is to 25. Now, so sometimes when you're going on different literature on the internet in books, you may see them have points on their periodic table for the elements mass number. This is where it's coming from, because the elements, some of these elements, you have different isotopes out there. So if you want to be specific in terms of the average mass, you have to take into consideration all the isotopes, right? And so for element Y, you would have been 23.3. The next question speaks to, and we spoke about it already, explain why the 2 isotopes of element Y have the same chemical properties. Now, they will have the same chemical properties because they will have the same number of protons, which means they have the same number of electrons, right? Since they have the same number of electrons, they are going to end up with the same electronic configuration. Remember, I said it earlier, really and truly, the electrons that are going to be involved are the outermost electrons, the valence electrons. And if you work out that of this Y, it's 11. So what's the electronic configuration? Definitely. So if you said 281, you're correct. So indeed, 1 electron is located in both the valence shell of these 2 isotopes, which means they're going to be losing that 1 electron, or that 1 electron is going to be the focus point of any reaction that either of these isotopes enter in. So, so they will have, sorry about that, they will have similar or same chemical properties. The 2 isotopes of element Y have slightly different physical properties. Identify with a reason 1 physical property that would be different in the 2 isotopes. So we know there's a slightly difference in the physical property linking to the mass. So the mass of the elements are going to be different. The mass of the isotopes, rather. They're different because both of them have different number of neutrons. The neutrons are the ones that influence the difference in mass number, right? And so due to the difference in the neutrons, you know that the mass or the weight of the element is the Y25 is going to be heavier than the Y23. So that's the difference in terms of the physical. The mass is going to be different. What is a radioactive isotope? Now, radioactive isotopes are isotopes that have an unstable nucleus. Now, because it has this unstable nucleus, what these isotopes will do is to basically, while to become stable, it will split. spontaneously. When it is split, when it is splitting, or when it splits, it's going to give off some energy or radiation or different particles. And so that's what we really call a radioactive isotope. So it's an isotope with an unstable nucleus that will split, and by doing so will become stable, and it will give off some amount of particles or radiation. The next question says, outline how radioactive cobalt-60 is used to treat cancer. Now, different radioactive isotopes are applied a lot in the medical field. And so, because we tend to try to improve our medicine every year, scientists are doing research. So we know cancer is one of the #1 killers right now, and it gets its position as a #1 because these cells, these cancer-causing cells, the tumors, they just replicate themselves, and that's how they cause the harm. Now, radioactive cobalt, the gamma radiation, what they will do is to basically get it onto these cancer cells, and it will basically destroy the cancer cells, because once you don't have the cells in your body to replicate themselves, then you can, relieve yourself of the cancer or slow down the process. So they basically put the person under radiation, gamma radiation, which is targeting the cells in the tumors where you have the cancerous cells, and it destroys these cells. List 3 other uses of radioactive isotopes and name a suitable radioactive isotope for each use. They use them for tracers. When you think about your body, scientists sometimes to find out what is happening, they can use something called iodine, right? And iodine is a tracer. You put it in your body like an ink, and it really shows you what is happening on the inside. So doctors can see where you may have a blood clot or something that is creating a problem, or even identify cancerous cells, and that would be good. Carbon-14 helps in carbon dating. Sometimes you're watching these documentaries and you're wondering, how the hell these scientists know these information, say that the animal that did there 1200 BC, the animal did there long time, and it has been living, or how it look, and they try to reform, because this helps, carbon dating helps with that. Uranium, they use uranium to help with power plants to generate energy. Plutonium, when you think about the artificial heart to get the energy, you wouldn't want to know that, unlike a clock, the battery powered heart, after they put in this heart inside of you, they have to cut you open, take it back out after 1 year, and then reinstall new batteries. That wouldn't make much sense, don't it? For cut into the individual, because each time you do the surgery, you're opening the individual to all diseases and any complications that can happen after. So those are some of the radioactive isotopes that you can list. There are a lot more out there. Just zero in on them, and you can add them to your list. Now, this was atomic structure. I hope the video was beneficial. I hope you learned a lot. I hope you're answering the question. I hope you're following. I hope you subscribe. You can leave a comment. So again, Buckle Down Tutoring Service. That is it. Thank you.